before we do our third realm of structure, we'll go back to a two-dimensional diagram, and we'll repeat that from an earlier lecture very quickly. But we'll still use the two squares. So if you take two equal diametered squares and stack them on top of each other, and then drop a larger semicircle at the midpoint of the larger square, you've completed an arch. So we'll shift over to these diagrams. You can see various forms of arches from history.
Now the next structure that we're going to talk about, we're going to go back and use the same two-dimensional, two-square diagrams from before. Now if you take one of these squares and you place two circles inside of the square that are the same size, same width, you put one on top of each other, one on top of the other. And then with the top one, if you draw a large semicircle going right through the middle of it, you will have completed an arch.
And at the point where the quote-unquote columns, really more so like piers for the arch, begin the actual arch proper, this is referred to as the spring point, where the structural energy of the arch begins and ends. It delivers the structural language from the load up above and carries it along the curve of the arch and then distributes it to the vertical element of the column down below. And the elements, the cut stone that goes along that radial axis of that arch, are referred to as voussoirs, until they reach the crowning jewel, which oftentimes is the decorative ornamental voussoir, referred to as the keystone. And the keystone is the link. So any one of those components that weakens, the arch would fail.
Now, if you take the center point of this arch and you continue it downward on the sides, you will now have what are your columns. These columns are what the arch sits on. So if you go to the top of the arch, right in the middle, this is called the spring point. This is the point of the arch where all of the weight of that arch gets dispersed down the curvature and down these columns and then back up. Now to build the arch, you start at the bottom with different cut stones. These cut stones are called voussoirs. So you take the cut stones and you stack one on top of the other, going up towards that spring point. Now just before you get to the spring point, there's going to be a section that is going to be missing. Right? This is one special stone that gets placed in there that's wedge shaped so that the weight of the arch can get dispersed through both sides of the arch and downwards evenly. This wedge-shaped piece of stone is called your keystone. It's the most important part because if the keystone were to fail, or it got misshapen or improperly made, the entire arch is going to fail because it's not going to be able to support the weight of the arch.
What the arch allows to happen is it can extend the space between the two columns. So look at your first sketch from today and see the relative proportion between the heights of those Doric columns and the space that's in between them. And then assume these are the two columns now and see how the generous space has doubled or tripled in terms of the width that's appropriate there. So by creating a different form out of the entablature, or the carried element up above, into something circular, we created a more structurally dynamic form that allows for more space to be in and less building to be necessary to house that space.
So one of the functions, one of the purposes of the arch is to create more space. And this happens because with the columns, your arch can then be built and create more vertical space rather than your doorway, your arch, being completed with a flat top. The flat top only allows so much. The arch extends that space upwards. if you take a look at your picture that you drew earlier in the day, you can see how this arch is extending that vertical space. And what it does is it allows you to have more space in that structure, but at the same time use less materials to build that space.
And even though it was evidenced in times before the Romans made this a central part to their architectural definition. So how that affects the space is then, again, moving up towards what we're trying to accomplish here. Now, because we're looking at this sort of obliquely, trying to draw a circle now in this axonometric projection, the simplest way to do that is to continue the next square up. And then if you wanted to bisect that, we find that at this point, and that point, and that point, the circle of the arch has to touch to fit within that square shape. So it ends up being drawn in like that to fit within the axon.
Now, the arch has been around for a really long time, but it wasn't until the Roman Empire that the arch really became a centerpiece in architecture. So we're going to look at this from a different angle. We want to draw another arch, but in more of a three-dimensional space. So we're going to take that bottom square and extend it backwards and draw a second square. We're going to cut that square into in half 4 different times. You can see at the corner points in which this arch is going to be built, right, that arch has to fit within the top part of that square to maintain its shape.
We go back to the back side here as well. This tops will be joined. So now, an arch, which is sort of singular in terms of its depth, an arch really doesn't create space, but an arch in its two-dimensional flat veneer pushed back into the z-axis creates a volume. And that structural volume is referred to as a vault. So we're blending then sort of like the two-dimensional arch with the three-dimensional vault in terms of moving through structural space here.
Now, the arch doesn't actually create three-dimensional space. An arch is only two-dimensional. And what I mean by that is that it only has width and it only has height. So if we want to give it a depth, we're going to take that arch on a flat surface. Right? So imagine drawing an arch onto a flat blank wall. You take the center of that arch and you push it back along the wall. You push in that wall. You're going to give it a depth. And it's going to look kind of like a tunnel. So when we create this tunnel, it's now called a vault.
Referred to as a barrel vault or a tunnel vault, depending on whether you're looking at an American historian or a British historian, in terms of just the language world. It would mean the same thing in terms of that tubular space that goes back. Now imagine, we won't draw this here because it gets away from our two-square diagramming, but imagine two of those squares create a cruciform shape and plan and they're going to intersect each other. When they intersect, the two tubes coming together, they share a common angular connection. If we do it in plan really quickly, if this becomes the floor plan of two barrel vaults, then they'll join and intersect the two vaults and create ribs or groins for those two vaults.
depending on if you're going to look at this vault from the American or the British viewpoint, it can either be called a barrel vault or a tunnel vault. The two words mean the same thing, it's just different countries that use it. So imagine you have two vaults, and they're going to come together. It's kind of like if you were to take two tubes and want to make them into a cross. You're going to have a point where these two tubes are going to have links that are common with each other. It's kind of like when two hallways meet, what happens when you have to turn a corner. Right? Now we're at the points where it meet, where you have that sharp corner, that sharp edge, that would be kind of like what happens with the vaults. When it happens in a vault, this connection, this section now becomes a rib or a groin.
Progression in terms of a major movement in architectural structures is the evolution of the arch proper and what its component parts can accomplish. Because as we diagram this now, we did one sort of linear section of how the arch can be used, pushed back in one dimension. But imagine if you wanted to have an arch diagram on the side of the wall of the structure as well as the front entry piece, so to speak. See an inherent problem with the Roman arch.
So now we're going to start to talk about what happens when you have two different arches coming together to want to make one specific part. This is where we're going to see our first problem with the Roman arch. So based on our drawing, we have our two different squares, our top and our base of that square. Alright, I'm going to show you what happens when we try to combine two different sized Roman arches and the problems that we face with it.
So that's the space we want to enclose again using the Roman arch on all four sides. So we've done this already. Done that already. Now starting with these same two corner points, we're going to put yet another Roman arch, which has to be inscribed in a hemispherical circle, a pure circle. So from here to here, it's going to rise up to that point, and this side will rise up to this point. So what you have then is the difficulty of having anything elongated and planned being resolved by the Roman arch. Because the width of the space will determine the height of the arch. And so one dimension is different in scope and scale than the other dimension. You'll have one arch rising up to a certain point and the other rising up to this point. And you can't marry the two in one continuous roof surface.
So if we go back and redraw our two square diagram, a three-dimensional square, you can see that all different sides of the square are different in its width. And it's the width that determines how high the Roman arch can be. So if we take our small sides of the square, on your top square and your base square, you draw those arches. It's going to be a little bit smaller than if we were to take the two long sides and draw those. So here you're going to start to see the problem of when we have the Roman arches and we draw them all in, it's going to be almost impossible to connect them all and still have one continuous, one smooth surface connecting it all together.